so today there will be a 45 minutes of theory, and then Tomas, who is the assistant for this course, will take over for the exercise session. Okay. So I think I only programmed this for 1 hour, Tomas, but do you think that, yeah, I mean, I put just 1 hour of course, so, okay, maybe in the worst case scenario, you can just send another invitation and set up a new.
Oh, you mean the meeting will expire?
Yeah, yeah, but you know, that's not an issue, because I think you got the email yesterday with all the addresses, right?
Yeah. So, okay, so just in case, I'll start a different meeting in the meantime.
I think that would be better. Yeah. Very good.
And send everyone the email.
Okay.
So in principle, I should be starting around 10, right? Yeah. Okay.
Okay. Okay, as there are not really new students joining us, I think I will proceed then with the course. This, of course, as you can imagine, this is a strange experience for all of us, but we'll have to get used to it. So let me summarize where we were from last week. So we're studying matrix models. Okay, so M is an n times n Hermitian matrix. Then we consider a potential which is a Gaussian piece plus let me use this normalization, a cubic piece, and I will treat this theory as any quantum field theory in which this is the Gaussian part. So this is the Gaussian part, and this is the interaction. Okay. And what we want to compute is the partition function of this model, which is the integration over all possible matrices, Hermitian matrices, and then we consider this action. And as we explained last time, we will do this using Feynman diagrams. But we are going to actually promote this to what are called double line diagrams, because we want to kind of keep track of the powers of n appearing in our calculation. So the propagator, it's now a double line like this. And you can think about this as the indices of the matrix, right? So this gives me, algebraically, this gives me a factor DIL, DJK. And then we'll have a vertex, which in this case is a cubic vertex, but in this double line notation, we're going to write it like this. So something like this. And then we label the lines like this, okay? So essentially, the structure of perturbation theory is very similar to what we did in the case of ordinary variables, but we all have now this double line notation. Okay, so so as usual, we want to kind of get rid of disconnected diagrams. There will be, as before, connected and disconnected diagrams. But the way to get rid of disconnected diagrams is to take the log of this object. So this only involves connected diagrams. And we can start like doing calculations. And then, you know, if you do this, oops, again. So what we will have is that, well, we'll have to expand the interaction part. And then here we'll have 1 minus, well, G3. Let me just, let me write it in a more unified way. So we'll have sum of K bigger or equal than 0. And then we'll have minus G3 over 3 GS to the K. And then trace of M cube to the K, okay? And the first non-trivial contribution, so this is summary of what we did before, but I guess some of you were not in the classroom last time for good reasons, so let me summarize then continue my summary. So the first non-trivial contribution appears for K equal 2. Actually, another way of writing this Z, so if you normalize by the Gaussian partition function, so let me just remind, okay, I will remind what ZG is. Then this is just sum of K bigger or equal than 0 minus G3 3GS over K. And then this is the average of trace M to the cube to the K in the Gaussian matrix model, where Cj is just the integral for the Gaussian theory. Okay, so this is our fundamental formula, and maybe I should be more precise, because again, this is not going to be a convergent formal convergent power series, or this is going to be a formal power series, so this is really more like an asymptotic series in the interaction coupling constant G3. Okay, so so as you can see, we have to evaluate this, and these are correlation functions in the Gaussian theory, and then, you know, we use Bick's theorem. Okay, or Bick's lemma. So so the first thing we notice is that this is 0 because of parity reasons. I mean, this is the same. This is the same reason why, you know, you have the moment of any odd power of x in a Gaussian distribution is 0. Just you know, this action, the Gaussian action, is invariant if we send m to minus m, and then any odd power of m, any average of any odd power of m will give you 0 automatically. So the first quantity that we should compute is trace of m cubed to the square. This is the first thing to compute. And in order to calculate this, we again use Feynman diagrams. So as you can see, this is trace of m to the cube was this vertex here, and we have to join these two vertices in all possible ways. So we have to do pairings of the legs of these vertices, but now with the proviso that now these vertices are thick. And then we get 3 types of diagrams when we do this. So the first diagram we get is the one in which we join. So so this is actually one of the few advantages of using the iPad like this. So if we join this like this, and this like this, and then we join this like this. So if we do this, we will get this diagram. Okay, so that's the first diagram we get. Now we can get two other diagrams, but by joining the three legs together. So we would have this, this, and this, for example. Okay. So if you do this, we will get this diagram. The last one we get is the one in which we do a similar joining to this, we cross things. So we get something like this. Okay, so this is a different type of diagram. Okay, and there are now various things that appear in this diagram. So the first thing we have to take into account are the possible number of contractions. So this diagram has, let me just check the number here. I think this one was three contractions. So there are three possible pairings. And this also, no, sorry, this has actually 9 possible pairings. So let me just correct this. So this was 9. Because the reason why there are 9 is because we have to join one line of one vertex with one line of another vertex. So there are 3 choices for this line, 3 choices for this line. This gives me 9. And this gives me 3 pairings and 3 pairings. And notice that both of them have to add to 6 pairings, which is 3 factorial. So this is what you expect from a diagram like this. But the main difference between these diagrams is the factors of n. So the way to count factors of n is to count the number of closed loops. So here we have 3 closed loops. So we have n to the cube. Here we have 3 closed loops, n to the cube. But here we actually have only one closed loop because the topology of the diagram is such that there is only a single closed line. So the power of n here is just n. And here you see the usefulness of this top notation, because precisely because we wrote the diagrams in this notation, we can distinguish a diagram. Oops. I guess you don't see my iPad anymore, right?
No, it went away.
Okay, yeah, sorry about that. Okay, it should come back now. Okay, sorry. I don't know why this, Anyway, okay, now we are back to the iPad, right? So you're seeing it, right?
Yes.
So here you can see that the fact that we have diagrams with double line allows us to take into account the powers of n. Okay, so this diagram has a power of n to the cube, while this diagram here has a power of n. Of course, if you thin the diagram, so if you thin the lines of the diagram so that all these lines collapse, you won't see a difference between these two diagrams. You would only see something like this. So the fact that you have diagrams with some thickness makes it possible to distinguish the powers of n. Okay? So that's the main message of this. And of course, we could keep doing this type of calculation for higher powers of G3 here. Okay, if you just keep more powers of G3 here, we will have to consider more vertices and you will have more diagrams. Again, by restricting to the free energy to the log of the partition function, you get just only connected diagrams, but you will get tons of connected diagrams of this type, and each of them with its power of n. Now, one of the reasons why we also introduce this notation is because in many contexts, we are interested in understanding what happens when n is very large. So n very large. So we would like to understand what happens, and we could think about this as sort of thermodynamic limit. Now, in statistical mechanics, we are often interested in what happens when n is much bigger than 1, because in this regime, typically theories are simpler, okay? So there are various reasons why you would like to be interested in n very large. And I mean, for those of you who are interested in the physical aspect of this story, essentially what happens is that this larger limit appeared in the context of chromodynamics, quantum chromodynamics. And quantum chromodynamics is a theory in which there is no control parameter. Essentially, you cannot decide that the coupling is weak or the coupling is strong, because this depends on the regime of energies that you are working on. So, for example, if you are studying quantum chromodynamics at low energies, coupling is always strong, whatever you do. So there is no real parameter of control, and then n, if you have a theory of quantum chromodynamics with n times n Hermitian matrices, then n is in a sense the only control parameter that you can incorporate in the theory, and then you can maybe suspect that in this sort of thermodynamic limit, the theory simplifies. Okay? So that's one of the reasons. But as we will see, there are other reasons. But first of all, if we want to understand what happens when n is large, we have to understand what is the power of n in each of the diagrams that you draw. Okay. So as we were saying last time, so let's associate to each diagram various quantities. The first one is the number of edges, the number of lines, which I'm going to call E. So this is the number of lines using the pairings. So for example, these diagrams have all 3 lines, okay? So you have one line here, another one here, and another one, oops, I'm not sure. Yeah, I think the connection is now getting a little bit slow, right?
Yeah.
Yeah. Sorry, I live in the countryside and we don't have cable here. Okay, so so I was trying to associate to each diagram some quantities. So let me try not to jump too much between here. So let's see if this can get stabilized. Yeah, I'm having some difficulty in getting my iPad screen to show in the main screen. It's not moving much now. Okay. It's actually frozen. Oh, okay. Now it's okay. Okay. So the edges are the lines in the pairings. So, for example, this diagram here has E equals 3, okay? And actually, all the diagrams that we wrote before, they all have E equals 3, okay? Now, if we have a general interaction trace of MP, then this will give a vertex with P lines. Okay, so you would have something like a like a wheel like this. So with P lines. We are going to write VP, the number of vertices with lines. So this is another characteristic of our diagrams. We are going to, if we only have one type of diagram, we are going to call V the total number of vertices of all types. Okay. And for example, again, this diagram has two vertices. Okay, so there's one vertex here and one vertex here. So here we have B3 equal to 2. Okay. And the last thing that we want to consider is the number, is H, which is going to be the number of closed loops. And very importantly, the number of edges and the number of vertices is typical of any diagram, thin or thick. Okay, so for example, you have a diagram like this, you can also give the number of vertices and of edges, right? This would also have E3 and B3 equal 2. Okay, but the number of closed loops is typical of thick diagrams like this one. Okay, so the number of closed loops, for example, for these vertices, for this diagram, sorry, is going to be 3. So here H is equal to 3. But for that diagram there, that we draw before, here H is equal to 1. And actually H is a topological quantity of the diagram, which distinguishes these two diagrams, for example, and distinguishes diagrams that when we make the diagrams thin again, would be indistinguishable. Okay? So these two diagrams, if you make them thin, they have just this topology. Okay, if you make them thin, they just make this topology, and here there is no H to distinguish. So H is really the quantity that is specific to diagrams of this type, diagrams which are thick. Okay. Okay, very good. So now what we want to do is to count powers of parameters in a diagram. As you will see, so each diagram comes with a number of factors, okay, that appears in the calculation. And the powers of the parameters that appear there only actually depend on these topological properties of the diagram. They depend on the number of edges, they depend on the number of vertices, and then depends on the number of closed loops. So this will be very useful to understand what are the possible factors that appear. Okay, so how does this go? Well, let's see. So there are various quantities that we have here. Remember that what are the parameters, first of all? What are the parameters? Well, there is a parameter GS, which we introduce as an overall factor in the action. Then there are the couplings corresponding to the trace to the MP matrices, okay? And then there is N. So these are the parameters in the theory. So how do we count the powers? Well, remember that GS is in the action, so it's here. Okay. And remember that the propagator, this is an equation that I didn't write today, but I wrote last time. The propagator has actually a power of GS. And so the two-point function in the Gaussian theory has a power of GS. And this is just because, you know, if there is this general fact that if you have a Gaussian interaction like this, then the two-point function involves the inverse of the matrix, okay? So this is something that we proved last time. So you have 1 over G. So here the matrix A contains 1 over GS, and when you invert it, you have a power of GS positive, a positive power of GS. Okay. So this means that if you have a diagram characterized by E, V, and H, each E gives me a factor of A minus 1 of this matrix, so it gives me a factor of GS. So I will have GS to the power of E. But every time we have a vertex, we have a power of 1 over GS, okay? Like, remember, like, so let me go up here. So see, this responds quickly. Good. So here you see that every time I have an interaction here, so G3 has always a power of 1 over GS, okay? So every time I have a vertex, I will have a power of 1 over GS, okay? So, so now it doesn't move. Okay, now it doesn't move again. So let's wait a little bit. So do you have any questions so far? I mean, I think you can also send questions by writing. I'm not sure how you can do that, but I was told that you can. Anyway, feel free to ask questions anyway. This would actually help me to get a little bit rid of this strange feeling of talking to my screen, which is the first sensation I have because I don't see you physically. So it's quite strange, all this. Okay, so again, this is, okay, now I see at least Thomas. Okay. Yeah, I think this type of connection is a little bit unstable, right? With the iPad moving like this. So
yeah, the lag is a bit unfortunate.
Yeah, because I mean, we tried yesterday possible ways of connecting the iPad to the Zoom, and we decided that this this air sharing was the simplest one, but it is probably not as fast as we. So let me stop the share for a little moment and then try to do it again. Okay. Okay.
Maybe you can also connect the iPad with a cable to the computer. Maybe it's better than AirPlay.
Yeah, but this didn't work well yesterday, right? We tried this with Thomas, didn't work very well. I mean, for some reason, the cable connection didn't work as good as we were expecting it. So
that's a pity.
Yeah. Okay, now we are back in. So, so as I was saying, every power of the vertices gives you 1 over GS. So there will be this power here, GS to the E minus V. So this is what happens for GS. Now what happens for GP? GP is very simple because essentially any, the number VP gives you the number of powers of GP. So this would be this. And then if you have many different P's, you will have this. And then N is going to be just the number of closed loops. So you will have the power of N to the H, okay? So that's essentially what you get in your, in terms of powers of the parameters. And now we would like to understand what happens when N is large, okay? So how would we think about this theory when N is large? And the first thing you have to understand is that every time in physics you have this game of taking N to be large, you have to be very careful because just taking N to be large, in a kind of obvious way, gives you sometimes quantities that do not behave well. And for example, you think about the thermodynamic limit. And when you do the thermodynamic limit, you have to take the number of particles to be very large, but you also have to take the volume of the system to be very large in such a way that the density is constant, right? This is one of the main properties of the thermodynamic limit. You cannot just take the number of particles to be very large and if you keep the volume to be the same, because if you do this, you are increasing the density of the system, and then you are changing drastically the physics of the system. So the limit of n going to n to be large is very special. In this context, if you want to have like a good limiting when n is large, it turns out that you have to take what is called the Toft limit. And in the Toft limit, you take n to be large, but you also take this constant that I introduced here, gs, to be small, in such a way that n times gs, which I'm going to call t, is fixed. Okay. One of the reasons why this is good, you will see it in a moment, because now I want to do the counting again here. So I want to incorporate this limit here. And then what I'm going to do, let me write again gs to the e minus v, and then n to the h. And then let's actually use the fact that n is related to t in this way. So you see that if I do this, I will gs to the e minus v minus h. And I will have t to the minus h, okay? Sorry, to the plus h, okay? So I get, when I do this, so remember that now I trade n by gs, so I will get this very specific combination e minus v minus h, okay? And why is this interesting? Well, because I can look at these diagrams, I can think about them as Riemann surface with holes. Okay, so the number of holes is precisely h, and then Euler's theorem tells me that this precise combination E minus V minus H is actually the genus of the surface, 2G minus 2. Okay, so the power I get here is directly related to the genus of the Riemann surface represented by the diagram. So that's a very important fact of life, that these kind of thick diagrams that Toph introduced can be regarded as Riemann surface. And then the power of GS is related to the genus of this Riemann surface. So let's actually go back to this diagram. So the diagram clearly represents, it's clear that this is a sphere. This is a sphere with 3 holes, right? And actually you can see that here E is 3, the number of vertices is 2, so there are 3 holes. So 3 minus 2 minus 3, which is this quantity here, is minus 2, which corresponds precisely to G equals 0. Okay, so this is really a surface with a Riemann surface, which is a sphere. Okay. Now, if you do this counting, that's now the most interesting thing. If you do the counting now for this other surface, so here E is equal to 3 again, V is equal to 2 again, but then H is equal to 1. So if you now use Riemann's Euler's relation, you get 3 minus 2 minus 1, and this is 0. So this means that this is a surface of genus 1. So this is actually a torus with 3 holes. Sorry, with 1 hole, because h is equal to 1. Okay. So with 1 hole. So, and then g equal 1. Okay. So you see how in this calculation that we were doing, we start like getting Riemann surface with different topologies, and the powers of the coupling constants will depend on the topology of this Riemann surface. Okay. So remember that we wrote this E minus V minus H. So this is ds to the 2g minus 2. But of course, this is also, remember that n times ds is equal to t, okay? And t is fixed. So this means that this you can also write it as t to the 2g minus 2, and then n to the 2 minus 2g, okay? So when you write it in this way, it's clear that when n is very large, when n goes to infinity, you know, the dominant contribution to the diagrams, to this expansion, comes from g equals 0. So that's very interesting. That's why this is sometimes called the topological expansion. If you look at all the diagrams that you can write in this way, you can see that diagrams which are a sphere topologically, thick diagrams which are spheres, are going to be dominant when n is large. And then as you add the genus to the surface, you will be suppressing their contributions, okay? So higher genera are going to be suppressed. So you have a hierarchy in which spheres give you the main contribution, spheres with holes, huh? But let me just write it like this. Then you will have tori with genus 1, which give you the, so this gives me a power n to the square, this gives me a power n to the 0, and then you will have the contribution of genus 2 Riemann surface, and this will be already suppressed like n to the minus 2, and so on. So you see that this is a theory in which the contribution of diagrams which have the topology of the sphere dominate, and then adding handles to the Riemann surface makes this theory decrease in importance, okay? And this is precisely what characterizes a string theory, okay? So you are not supposed to know what a string theory is, but in a string theory you have expansions in terms of Riemann surface, and the more handles you have, the more suppressed should be the contribution, okay? So this is what makes this beautiful connection between the 1/n expansion and string theory, for those of you who are interested into this. But in kind of more down to earth terms, what we have is that each, so the conclusion of this analysis is that each thick diagram gives a contribution which can be written, oops, sorry. As follows, as a certain number, which I'm going to write like AGH, and then you will have, you remember that you have here n to the h, okay? You always have n to the h in each contribution, right? You always have this contribution here. But if I trade this for this top parameter, so t is called, maybe I forgot to say this, is called the top parameter. So when you trade n for t, you will always have a power of t to the h. And then you always will have a power of gs to the 2g minus 2. So here, this is a coefficient, which is a number, and includes also powers of the GPs, okay? But what is interesting is that the dependence on T is in this way and the dependence on Gs is this way. So the free energy will, once you subtract, remember that here we are computing, so let me just make a little bit more clearer this. We were computing Z over Zg, so when we take the log, we will get something that, you know, we'll get log of Z minus log of Zg. So let me call this F minus Fg. And this is going to be a sum over all possible genera, G equals 0 to infinity of the diagrams. And then you will have a sum over all possible number of holes, okay, for each genera. And then you will have this double series in the top parameter and in GS. Okay, this is just a universal property that you will have. For example, let me give you, oops. Let me give you an example of this with the cubic matrix model. It is the cubic matrix model that we just. So F minus Fg here is something that we computed, right? Because coming from these three types of diagrams. And then if you write it in detail, you will get, you just put everything together, all the factors together that I wrote there. You will have GS, G3 squared times n to the cube plus 1/6 over GS, G3 squared times n. And then this is the contribution. Actually, let me tell you what this, what each thing is coming from. This is the sum of this diagram and this diagram. The contribution of these two diagrams. And this is the contribution of these twisted diagrams. Twisted diagram, sorry, there is only one. Sorry, it's always tricky to draw this diagram in spite of years of experience. Oops. Okay, so this is the contribution of this diagram. So you see that if I write this in terms of this top parameter, what do I get? I get 2/3 of G3 squared. And then I will have here n. So I write n equal to T over Gs. I get T to the cube and Gs to the -2. And then I will get here 1/6 G3 squared. And then I will get here T, and Gs times n is just T. Okay, so you see that there is no factor of Gs. So this is precisely in what you would expect from this general structure here. Okay, so this is a diagram which comes from G equals 0 and H equals 3. So planar diagrams, these are the diagrams which come from spheres are called planar. So you see that this is a diagram where G is equal to 0. So both these diagrams come from spheres, are both spheres with 3 holes. The power of T is the number of holes. And this diagram here gives you a contribution with G equal 1 and H is equal to 1. Okay. So you see that the different contributions can always be written in the form that I wrote before. So A GH, T to the H, and then GS to the 2G minus 2. Okay. So you see GS is what here counts the genus. GS to the -2 is genus 0, GS to the 0 is genus 1, and so on. Okay, so you can always write the expansion of the free energy in this form. Okay, this is just by counting of the parameters. Okay, in this form. But once you write things in this form, you can actually do the following. You can reorganize the sum in this way. You can decide, okay, let me just first sum over all possible numbers of holes here. I sum first over all the numbers of holes, and I will get a certain power series in T, and then let me add genus by genus the result of this operation. So let me do it more carefully here. So let me define Fg of T as the sum of H of these coefficients, AGH, T to the H. Okay. So this is a formal, as I wrote it now, this is a formal power series. And then F, the total free energy minus Fg. So let me just, this is just a normalization issue, but let me just make it sure. F minus Fg then can be written as a sum when G goes to 0 from infinity of Fg of T times Gs to the 2G minus 2. Okay. So, and this is the reorganization of the expansion suggested by this 1 over n counting or large n counting. So you see here, for example, for the matrix, for the cubic matrix model, we could write the first terms of this F0. So F0 of T comes from this term here, okay, will be this term here. So 2/3 of G3 squared T to the cube. And then there will be higher powers of T. And then F1 of T would be 1/6 G3 squared T plus higher powers. So by just considering the first, here you have to be careful about the way you think you organize the expansion. You see, we started this game by organizing the expansion in powers of G3. Okay, so more interactions meant more powers of G3. But now we have introduced this N or this GS, and then we see that we can reorganize the expansion not in terms of the number of interactions, but in terms of the topology of the diagram. So it's really like a change of paradigm here, because instead of using the interaction, the number of interactions in the sense of having a cubic interaction, for example, in the sense of in the example of the cubic matrix model, we are thinking about the topology of the diagrams that appear here. So this means that if you reorganize the theory like this, here in this F0 of T, there will be many diagrams with the topology of the sphere, but with arbitrary numbers of interactions. And when you reorganize the theory like this, all these diagrams, which involve an arbitrary number of interactions, contribute equally. Okay? So in each of these Fg of T's, there will be many diagrams involving an arbitrary number of interactions, but they all have the same topology. So it's a totally different reorganization of the theory. Now, if you do a standard perturbation theory, as we have been doing in this course, computing this series is very complicated, looks very complicated, because you will have to add, higher interactions. So for example, you will have here, if you now start like doing 3 interactions, well, you could get like a planar, so G equals 0 diagrams with an arbitrary number of interactions, right? You could have, for example, something like this. So you could have this, and this, and then this, and then I will have to add another diagram here, so another vertex. So you could have, oops, maybe. So I could have a diagram like this, right? So this is a diagram which has tons of interactions. Okay, you see we have 4 vertices here, but it's also planar. So this diagram would also contribute to this F0. Okay, this diagram, complicated diagram, also contributes to F0. So here in this series there will be infinite number of interactions contributing, but all coming from planar diagrams. So from the point of view of perturbation theory, this way of reorganizing your theory is not necessarily very useful. But it turns out, this is a surprise, that F0 can be computed in closed form. So this is like a big surprise, because what I'm saying is that also this quantity involves an infinite number of diagrams within infinite number of interactions. Still, it can be computed in closed form. And this is not an elementary calculation, but it's a remarkable calculation because you are actually incorporating an infinite number of diagrams in a single object. And let me also point out, from the point of view of convergence, it turns out that for the matrix model, these series are convergent. These are convergent series. So remember I told you that ordinary perturbation theory gives you asymptotic series, but actually this reorganization of the theory gives you convergent series. And you can actually find F0 in closed form for the cubic matrix model, for example, and you can see that has a finite radius of convergence, this power series. So this is a kind of very powerful idea, which goes definitely beyond the standard framework of perturbation theory, and has a very important role in modern physics, in modern theoretical physics. Now, I'm almost done with the course, so let me point out why is this okay. So these ideas are in a sense are more sophisticated. I think Thomas will give you in the exercise will give you some ingredients that go into the direction of how to compute F0 of t, but still is not a trivial calculation to do F0 of t. We are not going to do it in this course. But why is this relevant for topological field theory? Well, one of the reasons why this is relevant for topological field theory is because you see what you are doing in this way. You can think about this in 2 ways. You can think about this reorganization of the theory as giving me Riemann surface in order to reorganize the quantum theory. But this also gives you a quantum field theory way of thinking about Riemann surface. So you can think about this series as generating the possible ways of constructing Riemann surface with holes out of the perturbation theory of a physical theory. And actually you can use these techniques to enumerate the number of possibilities of constructing Riemann surface in this way. And you see, in a sense, quantum theory gives you all the possible ways of constructing Riemann surface with elementary ingredients. So in a sense, you could think about summing over all these possibilities of constructing Riemann surface as some sort of theory of quantum gravity, in which you sum over all possible ways of constructing geometries. And actually, these techniques of using matrix models can be used to construct quantum gravity in 2 dimensions. And quantum gravity in 2 dimensions is essentially a topological theory, and that's why this type of techniques appear in topological field theory in 2 dimensions. Okay, so that gives you kind of more direct link to the ideas, to the topic of the course. Okay, but anyway, this is also like a good, I mean, I think it's a good topic to know in itself. Also, the connection to topological field theory, I mean, I'm not going to actually make it more precise. I think it's quite an important thing in the big picture. of course, there are many uses of matrix models in modern physics, and another thing that you could suspect is that, well, why should we spend so much time with quantum field theories in 0 dimension, right? After all, this is our physical theories are in 3, 4, whatever dimensions, but not definitely 0. Now, it turns out that many theories in actual physical dimensions, like 3 and 4, can be actually reduced to matrix models. Okay? And this is a discovery related to localization, which is something that we will actually discuss in this course. So many quantum field theories which have supersymmetric properties can be reduced to these matrix models. So studying matrix models is not just an exercise in doing 0-dimensional quantum field theory. It can be also relevant to understand physical supersymmetric theories in 3 and 4 dimensions. So everything you learn in doing this quantum field theories in 0 dimensions made out of matrices is useful for quantum field theories in higher dimensions, provided they have supersymmetry. Okay. Okay, so let me point out that I put the first chapter of the notes covering everything that we have done so far in Moodle, so you can download it if you want. And then next week we are going to start something slightly more complicated. We are going to stay in 0 dimensions, but now we are going to add supersymmetry. Okay, so we are going to do supersymmetric quantum field theory in 0 dimensions, and this is already quite interesting. And essentially, we will be able to introduce the toy model to all topological field theories of cohomological type by doing this. Okay, so but in order to do this, we will have to understand to introduce supersymmetry, and I'm going to also to introduce, since I suppose that not all of you are familiar with this, we are going to introduce Grassmann variables, okay, in a kind of more systematic way. So introducing supersymmetry means introducing anti-commuting variables on top of commuting variables and doing integrals over anti-commuting variables. So in order to be self-contained, I'm going to give you an introduction to Grassmann variables, and then we will construct 0-dimensional supersymmetric quantum field theories, which will be the model for many of the theories we will study later on in the course, if we have the time to do that. Okay. Okay, are there questions, even in this strange format? So Jan, you are raising your hand, but how do I do in order to?
Oh,
yeah. Please.
I have a question.
Yes.
So for Riemann surfaces, then, and if you consider flat connections on Riemann surfaces, then you get this Atiyah-Bott symplectic structure on the space of flat connections.
Yes.
So do you know if it is related to this, maybe like the sub-leading term of the expansion or something?
No. I think you can actually incorporate the theory of flat connections on Riemann surface in topological field theory, but you need a little bit more work. I mean, this is more related to the kind of, I mean, you can think about flat connections on Riemann surface as some sort of dimensional reduction of self-dual connection on four manifold, right?
Okay.
And then you can construct a cohomological field theory in the sense that I will introduce later on for these flat connections on Riemann surface. But as far as I know, you cannot really do it with this flat for this. I mean, double line diagrams. I mean, it's not really related as far as I know.
Okay.
But you can do. I mean, you can do a lot of flat connections on Riemann surface using cohomological field theories in 2 dimensions. You know, there is a topological field theory in 2 dimensions which computes exactly intersection numbers for on the moduli space of flat connections on Riemann surface. Okay, and we are going. So in the next sessions, we are going to introduce this math-equivalent formalism that gives you the general pattern for that type of theories. I don't know if we are going to get so far. But you know, this is part of what we're going to do in the course. But this is not related directly to this large chain counting, as far as I know. Okay.
Okay. Mm-hmm.
Now, more questions. Maybe next day I will come back to, because this large chain counting is definitely very important. So I gave you, there are two versions of large N counting. One of them is using Riemann surface with holes. There is another version which is also very interesting, which is doing Riemann surface with no holes. Okay, and this is also very useful, essentially by using the dual graph. Okay, where instead of using the graphs with holes, we use triangles, and this is also useful because it makes a direct connection to triangulation or in general discretization of Riemann surface. So I will try to explain this next week, because usually in many books they explain this large N counting using closed Riemann surface and not open Riemann surface. So I think it's worth going through this. Okay. Okay, well, I really thank you for being there. Makes us a little bit less isolated in these strange times. So so as I said, now Tomas will do the exercise, and I will I will not attend the session of exercise if you don't mind. But I hope to see you all next week. So I will do as before. I will send you an email with a Zoom session so we can get together, and probably next week I will do 2 hours, and then we'll resume the course in this way. If there is somebody, I send you an email with to the people who were in Moodle, inscribed in Moodle. If you know anybody who is interested in following the course but was not incorporated in the first email that I sent, please tell this person to send me an email so I can put the email in the next round. Okay, if you are still in contact with anybody, with somebody else in this world. Okay. Okay, very good. I guess we can stop end the meeting.